Good morning, ladies and gentlemen. As introduced, I'm Grahame Martin, Global Business Manager for ALBA Power. And what we do is, anybody who doesn't know ALBA Power, we specialise in the repair and overhaul of gas turbines, predominantly aeroderivative. And for the last 15 years, we've been working as a company that overhauls and repairs gas turbines. What I want to do is explain to you a little bit of the background of ALBA Power, look at some of the inspection techniques that we carry out, look at some repair schemes that we're carrying out, and obviously some life extension to critical components. I guess what I have assumed for today is that everybody knows about gas turbines, everybody understands how a gas turbine works, and what the major components look like. Yeah? Yeah. It's fairly simple stuff, nothing too dangerous here. So, just a little bit about ALBA Power. As I said, we started in 2000, predominantly selling spare parts. So, we would buy an engine, disassemble it to components, and then place them into the marketplace. It was really customers who liked what we were doing and drove us to have a workshop where we would overhaul and repair gas turbines. So, right now we have in excess of 450 years combined manpower experience in Rolls-Royce specific gas turbines. That's just a picture of our workshop there where you can see that we overhaul different types of gas turbines. So how we're going to support legacy gas turbines for the coming decade. We have just signed an agreement with a company called Leaffield Logistics and Technical Services, where they are a UK Ministry of Defence surplus equipment supplier. So when the Royal Navy in the UK remove and get rid of their Tyne and Olympus gas turbines, they end up in Leaffield Logistics. Now ALBA Power has exclusive rights to these Tyne and Olympus gas turbines. Right now Leaffield are stocking over 21 Tynes in their stock, and combined between Leaffield and ALBA Power, we have over 30 Olympus gas turbines in stock in various stages. We've already set up supply chains to provide repair services, spare parts, and accessory overhaul, which I know is a concern for many navies, but we're already attacking it and addressing it and have already carried out some accessory overhauls. Competency of manpower is clearly something that needs to be addressed. We have a number of guys that work for ALBA Power who are ex-Royal Navy or in fact work for Rolls-Royce on the Tyne product itself. Life extension, you'll see there, coatings and repair schemes. We're going to come on to that a bit later on. But ALBA's ethos in everything that we do is maximum service flexibility. So if a customer wants us to look at something, provided it's not dangerous and it will provide a performance enhancer to the gas turbine, we'll definitely look at doing that and seeing how we can improve on the original designs. This is just some inspections that we carry out. It's rigorous inspections, and this is really the first part of any overhaul or repair, is to determine whether the component itself is still going to be suitable for further service life. So in the pictures here we have some nozzle guide vanes, HP nozzle guide vanes, going through fluid penetrant inspection. This is the lowest level of inspection that we do, but as you follow it through, this is the as removed component being applied with a die, and then you can see the developer has actually picked up a fault in one of the vanes here, and then we rectified that fault in the vane, and this is the overhauled component you can see in that picture here. So we have various and many rigorous inspection criteria. So fluid penetrant inspection, magnetic particle inspection, eddy current, X-ray, and there is a relatively new methodology called acoustic thermology, where you inject heat into a component and using an infrared high-speed camera, you can detect if there is any flaws in the component. Some of the repair schemes that we actually carry out are coming up in the next few slides. This is from an Olympus gas turbine. The dog ring, as it's known, supports the turbine entry duct onto the rear sections of the turbine section. So what you can see here is the mating, the dog itself from the dog ring with heavy frettage just on that edge there, and the receiving turbine entry duct location with also heavy frettage. Traditionally, these are components that may not be able to be repaired, but what ALBA have developed is repair schemes that can repair the dog and restore it to its original tolerance size. So here you can see the actual components being put in sight. So that's the dog after repair and its location within the engine. So you have the combustion chambers, turbine entry duct, and then the first stage nozzle section there. So after weld repairs and heat recoveries, it puts it back into tolerance, and we're talking quite small tolerance. So that gap there is around about 50 thousandths of an inch. And the frettage that occurs on the dog ring is because of the torsional forces as the engine starts and stops in this location. And of course, it allows this engine to be developed back into the field for another service life. This is another repair scheme that we've developed. Again, it surrounds about the Olympus, and hopefully you can see this location here. This elbow here is the air feed for the sealing and cooling air for the number 7 bearing on an Olympus. And what traditionally happens is in this location here, which is the static labyrinth seal for the forward first stage turbine labyrinth seal, is we get a degradation of the actual seal itself. But further on this unit, we have also developed a crack in this area. And this is the component after overhaul. So we can, through our jigs and fixtures, make sure that the cooling elbow is still in its correct place. It needs to be for when you locate the turbine section onto the delivery case of the engine. But also, we have also recovered the first stage turbine labyrinth seal area by coating it with a silver plating and then machining it back to tolerance so that it, again, this is another component that could be released for a full service life. So when we talk about full service life, in industrial world, that would be typically 24,000 hours of running, or for a marine application, we'd be looking at 13,000 hours of running. Just a bit more on component repair. This is a combustion chamber, and as you could see, that this combustion chamber has already been overhauled. We're able to replace that complete dish within the combustion chamber. This location here is a split sealing ring for the fuel nozzle so that you can maintain your airflow through the combustion chamber. And what we can actually do is this area wears. You get lateral movement on the sealing ring, so what we can actually do is we can weld that location up and machine it back so that you have, again, back to original tolerance, the sealing ring capability. This is really quite an important piece, although it looks very small. If this piece comes out of the combustion chamber, it will destroy the turbine. There is no doubt about that. Just in that picture here, what that's really demonstrating is that we can replace any of these sections. It's a modular piece of equipment, the combustion chamber, and we can replace the heads, we can replace the air cooling system and the dilution system, and also just on the edge, the interconnectors. So there is 8 combustion chambers sit around the engine. The interconnectors are a common place for wear to take place. It's known as frettage, and we can recover that completely. Just on the forward, this is the forward end of the combustion chamber, and this is the rear section of the combustion chamber. We can also apply hard face coatings to these areas. So the air intakes now coming from the LP and HP compressors comes into the forward end of the combustion chamber. There is a location there which unfortunately also wears, but we can recover that, again, with a hard facing. And the same at the rear of the combustion chamber, there is 2 half clamps that we saw in the other picture when the turbine section dog ring was being fitted. There is 2 half clamps hold the rear of the combustion chamber in location. Again, we can recover that area by flame plating and machining back to tolerance. This is a combustion chamber that we had come in, and it was due to the fuel that the customer was using. He was running on a mixture of diesel and natural gas, and it developed a vibration in the engine. Oops. It developed a vibration in the engine which made the securing strap and boss snap. What we were able to do was recover this whole area. That's the combustion chamber there in the number 5 position. We were able to remove that head completely, install a new head, overhaul the rest of the combustion chambers, and obviously all of the close tolerances again were recovered to allow this engine to be put in the field for another service life. This is a fault within the compressor area of a gas turbine where the early stages of the stator blades, so the stationary stator blades that guide the air through the compressor, are located in an aluminium casing at the back there. When that aluminium casing wears, due to the starting and stopping of the engine, you get movement within the actual stator vane itself. What it actually, because the tolerances are so close, once it actually moves and falls into the path of the compressor, you can see the kind of defects and faults that you can get from a compressor. So this is what we did. This is exactly the same compressor casing, the same compressor rotor. We were able to recover the casing land where the compressor stator is located. We obviously had to replace the stator itself because it was beyond repair, and also the blades within the compressor itself were replaced. There was no recovery for that amount of damage. But as you can see there, this is our dynamic balance machine, balancing around 2 planes. Right now we're balancing to less than half OEM limits. So whatever Rolls-Royce are recommending right now, ALBA Power are doing it to half that extent. As you can see there is just some components that we can't recover. This is pretty severe damage. Again, I'm hoping everybody understands what we're looking at here, but that's basically the LP turbine section of an Olympus gas turbine, where the customer, through lack of maintenance, allowed one of their fuel nozzle shrouds to come off, and it only has one way to go, and that is through the turbine section, leaving nothing left. We can't recover it, but of course we have a huge amount of stock, so we can replace these turbine blades, balance the machine, and then get it back into service again. This is a huge subject, but what I hope today is to give you an overview of what this actually means, and it's full solution rejuvenation. And basically what it means is that through various heat treatments, we can take turbine blades, put them through the heat treatment, realign the grain structure, so you're actually, the effect of the heat treatments dissolve the precipitates of the actual blade itself, realign the structure to as good as it was when it was a brand new turbine blade. We can go through this process up to 3 times, and basically it means that you don't have to buy new turbine blades every time you overhaul your gas turbine. We can rejuvenate them for a full service life. The graph on the right-hand side there is really about what happens after the blades have been rejuvenated. So the full strength, you can see at the far end there, the full strength is back in the blade after full service rejuvenation. This is where the OEM determines the strength, and the stress rupture test would take place, being allowed to achieve at least 24,000 hours. This is strengthen the material after 24,000 hours. Sorry, this is new blade here. And this is after 48,000. And then again, once you've had the full rejuvenation process, the strength and the realignment of the grain is removed from the blade. So effectively, if you hear the term creep, which is mean the blade is basically getting bigger, longer, you're losing the tolerances, we can recover that through this process. Up to 100,000 hour operating hours. This is not a new process. This process has been going on for the last 25 years. Relifing of critical components. This does take a change in mindset. The OEM of this gas turbine will tell you that turbine discs need to be changed at certain times, at certain hours. But what we can do through modern computer modeling is assess the stresses and the centrifugal forces being applied on the gas turbine discs itself. We can check to make sure that there is no cracks within the disc, or in fact any initial flaws when the disc was manufactured. The turbine discs are different from turbine blades. They don't suffer from high service temperatures, providing the cooling for the gas turbine is okay. The discs themselves suffer from more stresses and strains, rotational forces, as you can see in these pictures here, rather than high temperature fatigue. So what we're looking at is the safe life approach, assessing as I said, the design elements, the temperature operating envelopes, calculating the safety factor. We don't want to put anything into a machine that's going to fail or not be able to last in time. And obviously that'll give us a calculated minimum creep, fatigue, crack initiation point, which is determined as the life of the turbine disc itself. We use a subcontractor for this. This is not ALBA Power that does this. But again, just to give life extension to the gas turbines, what we're looking at is additional coatings to areas that are not traditionally coated, using very modern technologies, very modern techniques. So the coating that we're actually using on a cold end compressor is K900. We're using an additional undercoat, which is the IP seal coat. And again, it's to protect against corrosion and give life extension to the components. Also, the discs and the spacers are also coated. And if you can just see that there, that is the front labyrinth seal. Traditionally an area that suffers from high corrosion. We're coating this in a Cermatil coating as well, just to make it last longer. Exactly the same in the turbine sections. We're using the aerospace grade coating for turbine blades and nozzle guide vanes, IP1041. And again, you can see the labyrinth seal there being coated in a Cermatil coating, all in the effort to protect it against corrosion and make it last longer. Thermal barrier coatings, I'm speeding up a wee bit because I'm running out of time here, but thermal barrier coatings, again, it's just to try and reduce the temperature, surface temperature of real hot areas within the machine. In this area of the gas turbine, we're looking at around about 1,000 degrees centigrade, and if we can reduce the surface temperature in this area and also the effects of hot erosion, then again, it's a protection of the component to get it through to the next service interval. Not only in nozzle, discharge nozzles and entry into the turbine section, but also in combustion chambers, so we can help protect the combustion chambers through its service life as well. We are obviously looking at very old technology gas turbines. They're designed in the 1950s, 1960s, and as well as looking at life extension of the components, we're looking at ways that we can save them in service from damaging themselves. So we have come up with a concept idea on the Olympus Air Start in particular to provide a life extension to the deep internal components, which would also be feature selectable. So what we have is a high temperature, high pressure air control valve being controlled by a Micrologix controller, and we're looking for the two-way feedback. So effectively what that means, in normal situations when you just want to have a relatively low start speed, we can control the ramp rate with the microcontroller and has less impact on the internal bevel gears. Or if you were in a combat situation, we can have the engine start as quick as you want it to start. So that's some of the things that we're just looking forward to. And as a concept at the moment, so we're looking for ways in which we can get that into ships. So hopefully you managed to understand my accent. Hopefully you understand a bit about gas turbines now, if you didn't before, and maybe also a bit about ALBA Power. But if anybody's got any simple questions, I'd be delighted to take them.
What about the alloys of your blades? Are they nickel superalloys or other?
They're a nickel-based superalloy. So
this is the type of blade you are
traditionally is the type of blade we're working with.
And the second question, do you care about stress measurement?
Absolutely care about it.
Not modeling, but measurement in the blades and the steel component.
Yes, absolutely. So, although we're doing modelling and through the rejuvenation process we can reclaim the turbine blades, we are assessing them continually for future lives. We've been doing this process, although the process has been going for the last 25 years, we've been doing it for the last 15 years and had great success with it. That's a very tough question to answer. It does depend on the gas turbine itself and the condition of the gas turbine. But to try and answer your question, we would traditionally be at least 50% less than the OEM. And the warranty life after the engine has been overhauled, not repaired, is at least 6,500. If we talk about time particularly, at least 6,500 hours or 2 years or 5 years in storage. For the Olympus, we would release that with 13,000 hours. Again, 2 years or 5 years in storage. The location in the ship of where the gas turbines are situated kind of excludes any major inspections with non-destructive testing being carried out. If the machine is out of the ship and we have it in the shipyard, for example, then we can do on-site. Fluid penetrant only is what we would recommend. If it's going to be anything more than fluid penetrant inspections, we need to take the machine back to the workshop.
Based maintenance, you said that you use subcontractors. How do you work with them to maximise the life of the engines and use the data that's been built up for Rolls-Royce on the operation of these units?
Maybe something I should have explained right at the start is ALBA Power is a completely independent company. Our association with Rolls-Royce is that we buy parts from them and we also sell spare parts to them. But in terms of maximising the life, well, you can see from the full rejuvenation process, you can get 100,000 hours out of turbine blades that are traditionally only supposed to last for 24,000 hours. So we control our subcontractors. They are either ISO 9000 approved or Rolls-Royce approved, but we keep and maintain control of them. And you're right, we do analyse what we have back from them. We've been going for 15 years, never had a warranty claim in 15 years.
When you fix a combustion chamber that was wrapped from the use of oil or natural gas, how did you be assured that the rest of the chamber didn't have the crack or tendons for crack?
Well, the one that you saw, we exchanged the head of the combustion chamber on. All other 8 were thoroughly inspected using fluid penetrant inspections, so we could make sure that there was no other cracks present, that the actual parent material of the combustion chambers was in a good enough condition to be able to replace the head, and also that the material thickness on all of the combustion chambers was in a position where they could be overhauled and put in a full service life. Just to explain a bit, it was an offshore installation, so it was an oil platform, and the machine is set up for dual fuel, so they can run on either natural gas or diesel. But what actually started to happen was they introduced sour gas into their natural gas side of, and the engine reacted badly to the sour gas.
Two quick questions from me, and then I'll let you go. You talked about the full strength instrumentation, and I had one question. You specifically talking about the blade. Yep. Do you do the same thing when you do other parts, like you remachine something that was circular or something that was pocket again? When you treat it in molding and the property of the metal might change, so do you go through the same process, these tests to make sure that?
Yeah, absolutely. Regardless of the part, and they are proven repair schemes, so by silver plating, we know that there's not going to be any material mismatch or interaction that is going to be adverse to the repair itself.
And one last question here. When you did this, you talked about having tolerances that exceed your initial. You do the full standard transportation. My question is, when you talk about tolerances, do you guys go to this to the point of failure and then you just touch down?
What happens is that we have turbine blades that have got damage that can't be recovered, and they're matched with the set that is removed from the engine, so they're of comparative life. And then what we do is we rejuvenate the set of turbine blades, and the material that can't be recovered is put through the same processes, and then we destroy it to see how its properties look, and that's how we know the grain structure looks like.
And then you say at the yield, what the yield is here, so we're knocking down by 20-30% or some sort of. Because you don't say it's life until the yield. We don't want that.
No. The rejuvenation process can only be successful if you do it on a time basis. So if we know it's done 24,000 hours, we can rejuvenate it. It can go back and do another 24,000 hours. We can bring them back, rejuvenate it again. At that point, we would probably need to destroy a blade to see how it's reacting.
Okay, thank you very much.